Our next notion is to take these power series, as if they weren't bad enough. Now I want to throw in the notions of derivatives and antiderivatives with power series. The good news is they work very straightforwardly. We saw that when you expand these things out, they tend to look like polynomials. It turns out that when you work the derivatives and the integrals with them, they tend to work like polynomials. In fact, we're going to see that's going to happen with our subsequent videos, subsequent lessons. So, suppose we have a function which is a power series. Remember, depending on the value of x, and we substitute the value in, this will converge or not. This is a function of x. We need to assume, in everything we do here with these notions, we need to assume the radius of convergence is greater than 0. Remember, a power series, exactly one of three possibilities. It converges only at a particular point, it converges on an interval of finite length, or it converges on the entire real number line. What we're talking about is category 2 and category 3. We are not talking about the circumstance where the only place it converges is at a single point. Where those are right out, we're assuming the radius of convergence is non-zero, it's bigger than 0. So we are either in category 2, where it's an interval of finite length, or it's in the category 3, where the interval is of infinite length. Both of those are larger than 0. All right, so let's assume that's the case. Then, the derivative is this. Power rule. That's one of the reasons this is called a power series. Power rule, the derivative is just the power rule. The power rule is, this is with respect to x, the derivative is being done with respect to x. Now with the derivative, x is the variable, n is the constant. When we do the limit, n is the variable, x is the constant. But with the derivative, x is the variable. So n is a constant. This is just a constant multiplier multiplying along. The derivative of that expression is n times a sub n times x minus c to the n minus 1. And so the sum of these things is the sum of these things. And earlier I made a mistake when I wrote this, but when I wrote this on a previous example, I had to fix it. But I'm writing this on purpose here. Look. Look. When you do the derivative, not only do you lose an exponent, you lose a term in the expansion. When you do the derivative, you lose things. That's the way to think of it. That's going to come into play here pretty soon. When you do the derivative, you lose things. You lose an exponent, you lose a degree, and you lose the n equals 0 term. All right? If n is 0, this is 0 and the term falls out anyway. Think of it that way. So when you do the derivative, you lose a degree and you lose a term in the expansion. The antiderivative is, go back to the original, it's the power rule. Add 1 to the exponent, divide by the exponent you just created. This is a sub n, x minus c to the n plus 1, divide by n plus 1, plus a constant of integration. This c is not the same as that c. This is a capital C constant of integration. This is lowercase c, center of the expansion. These are not the same value of c. If you like, some people put a k. Our textbook puts a capital C, or you can call it C prime, or some people call it K or a D, but these are not the same C. This is the center of the expansion, center of the power series. This is the constant of integration. They're not the same value. But I do need to put on, I forgot my sequence here, my sum. You do not lose, right? When you do the antiderivative, you do not lose, so it stays at 0. Notice that if n was, you don't lose, you don't say n equal -1, because then this would be undefined. So you gain, you increase this. You lose a term, but you don't pick up an extra term in the antiderivative. All right. So if you have a power series, this is how you find its derivative. This is how you find its antiderivative. Use the power rule. And here's the bit. The radius of convergence doesn't change. The radius of convergence does not change. That is to say, if the radius of convergence of the original is 1, then each of these has a radius of convergence 1. If the radius of convergence here is 5, then each of these has a radius of convergence 5. If the radius of convergence here is infinity, then each of these has radius of convergence infinity. The radius of convergence does not change. However, if you start off with an interval of convergence that is finite length, then the endpoints of the interval. If you have an interval that is finite length, if you do have endpoints of the interval, whether they're included or not, the endpoints of the interval might change. And the key word is might. You don't know going in, so there's nothing for it. You got to plug them in and find out. All right? So there, if it's finite length interval, you can find the antiderivative and the derivative. The endpoints might change. Now, what is always the case is this. You lose things when you take the derivative. So if you take the derivative, if you have endpoints on the original function, when you take the derivative, you might or might not lose some of them. When you take the antiderivative, you might gain them. All right? So you must check the endpoints of the interval of convergence if it is the finite length scenario. So given any power series, this is how you find the derivative, this is how you find the antiderivative, and then you can check the endpoints of the interval of convergence independently.